Okay, so in terms of my lesson plan, I'm just going to spend the first little bit just finishing off the geology portion, which is just going to focus on the soils, the type of soils you'll see, or everything related to soils, I guess. So we've mentioned these words before, weathering and erosion, but keep in mind the different things. So weathering is kind of like the damaging of rock, almost, the breakdown of rock. You'll see later there's two types of weathering, mechanical and chemical breakdown. Whereas erosion is the transportation of these rock particles, in other words, soils, right? So here's how I've got my little tree diagram set up in terms of the weathering of rock. So we have the mechanical or physical breakdown, as well as the chemical, which I'll cover on the next page in my notes. But this is just the mechanical one so far. I'm going to zoom in a little bit on this first one. So when you're talking about de-stressing or unloading, kind of two words for it. So you can kind of see there's this top layer of rock confining this bottom layer. And this term, confining pressure, is actually kind of exclusive to when we're talking about geotech, essentially. You're not going to see it in the structures or anything. So confining just means it's kind of holding it in place, right? The soil's holding the other layer in place. But when you remove it, which is what the second picture is, essentially, because it was previously in equilibrium, it wants to expand and uplift this bottom layer, which is going to form this kind of strange pattern called sheeting joints, or an exfoliation dome, essentially. So that's everything involved with de-stressing and unloading, which is a type of mechanical weathering. Okay. The next type is landslides or gravitational creep. So I've kind of grouped these together. Landslides, I think most people have a fairly intuitive understanding of this, of what a landslide is. But gravitational creep is essentially a landslide, but happening very slowly. Okay. So here I've included a couple examples of landslide configurations, and creep is this one on the bottom right, which is just like kind of minor slow effects of landsliding. So thermal expansion is when there's heat effects on a rock, say from the sun or like change in weather or something, and it causes it to expand and contract. That will cause some level of mechanical weathering. The next one here is freeze thawing. So essentially when you've already got some cracks in a rock, which is pretty common already, and water seeps in, and then there's a change of environment which causes that water to become ice, so it becomes much colder, temperature drops or something. Ice is naturally less dense than water. In other words, the particles to form ice will want to expand, right? And that expansion in volume is going to enlarge, is that a word? It's going to make the cracks bigger, basically, right? So that's what freeze thawing is. These next few are fairly intuitive, so I haven't done much except drawn a little picture to describe them. So extreme rainfall, or we've talked about rainfall being a type of mechanical weathering before, but yeah, extreme rainfall is just like that, but to a much faster rate, essentially. Earthquakes, you can imagine, it's going to cause all sorts of mechanical weathering. Growth in tree roots, same thing. Tree roots can, over time, grow and then damage rocks and cause cracks in them and all sorts of damage, which is what weathering is. Swelling of clay and water in joints is kind of similar to freeze thawing, except instead of water turning to ice, it's that clay expands when it's exposed to water, unless it's like fully saturated. So yeah, it just gets bigger. So again, it widens that crack in joint. And then lastly here I've included honeycomb weathering, also called helicity. And this is kind of due to saltwater effects. So actually, in the Bronte FAQ PDF that Kurt's put out for your assignment, there's an example of honeycomb weathering, which is quite interesting, and there's quite a lot to talk about. So if that's your section, then you're in luck. Actually, I just looked it up between my classes, like my 9 a.m. class and this class now. Honeycomb weathering has some chemical effects as well, which is what we're going to talk about in a bit. So it's kind of mostly mechanical weathering, but it's like a complicated interaction of mechanical and chemical weathering. It's basically when salt, water, and wind kind of blow onto the rock and then causes that rock layer to get damaged or weathered, right? Yep, does anyone have any questions? Okay. Next, we're going to talk about chemical weathering. So in terms of where we are in this tree diagram, weathering a rock, we're following this path down to the chemical portion. Here at the top, I've just made a little note that chemical weathering generally is accelerated by mechanical weathering. So what mechanical weathering is, in general, it's going to, so you have a rock, you have a crack in it, and mechanical weathering processes might expand that crack or do something to the top. And if you think of this in 2D, like how I've drawn it, it increases the perimeter, right? And so in other words, in 3D, it increases the surface area of the rock when mechanical weathering happens. And chemical attack on rock, or chemical weathering, basically will be accelerated when there's more surface area, right? So, for example, due to groundwater infiltration, something like that, it's going to be accelerated due to the mechanical weathering. So here I've listed a couple of chemical processes which happens. Carbonation is one of them. So carbonation is when you have carbon dioxide, water turns into carbonic acid, which is organic, what do you call it? Some sort of acid, I'm not very good at chemistry. But it dissolves limestone when it interacts with limestone, for example. And this is how limestone caverns form. So if you haven't picked a topic yet for your research assignment, maybe you can look into limestone caverns and how they form. It's essentially due to this chemical weathering effect. Oxidation is basically rusting. So there's dry oxidation and wet oxidation, and the difference between them, chemically speaking, is that wet oxidation will also involve water, basically, in the equation. And typically, when we talk about rusting, we're looking at the effects due to iron, so like the iron minerals within rock, and how they're affected by it. Hydration and hydrolysis. For those of you who are better than me at chemistry, which is probably most of you, you'll know what this is. So this is like something to do with water. But basically it creates these flared slopes, also called wave rocks. I've flagged as an example. So again, if you haven't picked your assignment topic, your research assignment topic, maybe you can look into flared slopes, wave rocks. There's very interesting effects going on there. And lastly, I'll put it down acid rain as an example of both chemical and mechanical weathering. Mechanical because acid rain, like rain, would impact onto the rock, some sort of force, and then damage it. And whatever residual chemicals it leaves on could interact with the rock and damage it that way too. Yeah. Does anyone have any questions? Yeah, cool. Next, we're going to talk about erosion. So again, erosion is to do with the transportation of rock particles, or in our case, we're talking about soils, right? Like the residual soils from weathering and how they're moved around, right? So here, the first one I flagged is alluvial. So this one we've probably heard earlier in the course as well. Alluvial is just another way of saying river. One way to remember this is like panning for gold back in the gold rush days. From a river, it's called alluvial gold, right? You're sifting or whatever for alluvial gold. Alluvial soil, by the way, just randomly put down as a fun fact, is fertile. It's quite fertile for agriculture. So there you go. We have types of streams, which is your rivers. You have your meandering streams and your braided streams, and these two have like kind of different properties. And it'll tell you a little bit about how the soil and the water properties will also be there. So on the left here, we have a meandering pattern. This kind of looks like Bloom's Tower Defense, where it has like a very uniform river mouth the whole way, river width. Whereas braided on the other end of the spectrum is kind of very ununiform. It has like higher velocity. The water's going much quicker. There's more energy in this whole system than in the meandering river. And so, in general, there's like kind of areas in a meandering river, but key ones which are flagged is the deposition area and the fact that erosion happens due to the water carrying the particles, right? Meandering streams will also have finer grained particles, whereas braided streams will have coarser grained particles. In terms of the variability of the water, braided patterns you might find will have a high variability in the waters and higher velocity. Okay, sorry, that was a lot about alluvial. By the way, I'm kind of just scratching the surface in terms of what like this topic's about. If you want more details, you can look at Kurt's notes, which are more detailed, but I think I'm covering the key things which are going to be in this, I guess, week's topic. So we talked earlier in the mechanical weathering portion about landslides and gravitational creep, right? So if you think about a landslide, it kind of has this weathering and this erosional effect where the rock is damaged and it gets carried, like it gets moved or whatever, like the rock particles, whatever. So in terms of colluvial residual soils, it's just soils which have been displaced due to gravitational creep or landslides. That's it, right? Marine soils can be found at the bottom of ocean beds. Just keep in mind this is different to alluvial soil, even though they're both related to water. It's just kind of like, anyway, I'll just leave it at that. Glacial soils, it's basically from, okay, so this picture on the left, this is probably one of the more important features of glacial soil. We have two situations of valleys. The one on the left is where a river runs through this valley and it ends up with this kind of V-shaped cross-section, right? Whereas one which is, I guess, like, I don't know how to explain this one. One which is like kind of iconic for glacial soils is this U-shaped valley, essentially, right? Characteristic, that's the word I was looking for, sorry. It's this U-shaped valley, it's called a glacial valley. And yeah, the way that this can kind of be explained is like, just imagine like back in the Ice Age, everything's covered in snow. If you imagine how a snowball works, or like a rock rolling down a hill, the snow will accumulate on that rock and become a big boulder, and that keeps happening and then carves out this kind of shape, which ends up with this U-shaped glacial valley. So that's probably the most important thing you need to know about glacial soil. And then we have aeolian, that one. It's wind erosion, essentially, right? And you heard of the movie Dune, right? That's where, like, dunes are the patterns left behind by aeolian soil, right? So we have different types of dunes here. And before we were talking about cross-bedding in like sandstone. That cross-bedding pattern is actually characteristic of aeolian soil, which has been lithicated to sandstone. So that's where you get the cross-bedding from. Yeah. Does anyone have questions? Okay. We're gonna keep going, right? Trust me, there's only one page of this before you go to our quiz. You'll do a small soil mechanics review, okay? So again, this is dipping into the second half of the course, right? Everything I was talking about before is just geology. Don't worry, it'll be simple. There was like, don't. Okay, so soil, right? How we treat it in civil engineering, and when we're looking at the physics of soil, is basically we treat it like they're a bunch of small solid particles with interactions with water, unless it's completely dry, essentially, right? So that's why it's good to know about your solid mechanics and your fluid mechanics before going in soil, and that's going to carry through into the second half of this course, right? So, yeah, like mathematically, we're going to kind of consider two broad types of soils. Sands and gravels, obviously there's like other, like silts and stuff as well. But these types of soil are governed by shear strength via friction. Like they get their strength in shear through friction, right? And then we have our clays as well. And clays basically are sticky, right? Like an adhesive. And their shear strength comes from their cohesive property, the ability to kind of stick together, right? That kind of makes sense, right? So that's soil in general. So shear failure is probably the most important type of failure when we look at soil or geotech design. And we have this thing here called our failure plane, which is kind of the shape which the soil will slide down or along, right? And here we have a footing, right? It has like some amount of force from a structure or something above it that is like holding up. And these kind of weird looking arrows denote the direction of shear stress, which is basically trying to resist this external force. Yeah, it's trying to resist this external force. And that's basically what all of our calculations will be based on today, okay? So Moore-Coulomb criterion is basically the formula which we're going to follow for a lot of the questions today. And tau F, sometimes also simply just called tau, denotes the strength of our soil, which is that thing in blue there. C is our soil cohesion. There. And phi, which is the angle, the friction angle, is, yeah. So these are all like C and phi are material properties for the soil, and they're going to be given in the question. So we're going to have to perform undrained and drained analysis, and basically the difference is that undrained analysis, you can assume that water effects are going to be in play in terms of water can't leave the soil, basically, right? Whereas drained analysis is where water can leave the soil or freely flow through the soil. So these will have two slightly different formulas. They're both based on this one I'm showing here. It's going to look like this, right? The undrained one, the C is going to have a subscript U. And the phi will also have a subscript U, right? So those are our two material properties. Whereas the drained one, you're going to have C dash. So the dash is going to denote our drain case. Also our stress, instead of looking at the total stress, which is just sigma or sigma n or sigma t, we're just going to have sigma dash, which is our effective stress, if you remember from soil mechanics. And then we're also going to have a dash on the phi there, right? So everything has got dashes for the drain case, and then everything has a subscript U for the undrained case, right? Except this one. Okay. So let's talk about this component there. That's the normal stress. And normal stress, in general, is your normal force over area, right? And so what the forces that we have to look at are the forces acting on the failure plane, right? And then A is going to be the area of the failure plane, or the area, yeah. So we're just going to be using sigma if it's undrained, right? But if it's drained, we're going to be using sigma dash, right? So sigma dash does extra steps. The first one is that you have to calculate the pore water pressure as well, or you have to calculate the normal stress and the pore water pressure and subtract them off each other. The pore water pressure is going to be the unit weight of water multiplied by the depth at the middle of the failure plane, right? Let's talk about material properties quickly. If you remember what specific gravity is, it's how much heavier our material is than water. So if it's 2.65, just means that our soil that we're looking at is 2.65 times heavier than water, right? If you're over concrete, if you've done concrete before, it's 2.4 or 2.5, something like that, right? Yeah, and then unit weight is basically going to be this number multiplied by 9.8. G in this course is 9.8 meters per second squared, basically. In different courses, it's going to be a different number. I think in soil mechanics, this is 9.81, or like at least in fluid mechanics, it's 9.81. In concrete, this is 10 for some reason. Anyway. But yeah, but usually you're just given this number, so you don't have to do this extra step. Okay, let's talk about weight. So weight is going to be your unit weight multiplied by your volume, right? Sorry. Which kind of makes sense because weight is going to be in kilonewtons. Unit weight is going to be kilonewtons per meter cubed, and then volume is meters cubed, right? But so that's like, say we're looking at this rectangular prism on the right. That makes sense because we can multiply all the dimensions of that rectangular prism to get the volume. But something to understand about how we're going to do it in this course is oftentimes you're going to be doing your calculations per meter into the page. It's called per meter run, okay? So we're going to do the same thing, except we're only going to care about this cross-sectional area. And this number we're going to end up with is going to be kilonewtons per meter run. Right? Should write that down. Right? Just spell meter wrong. I don't know. But yeah, we're looking at basically doing all our calcs as if it was 1 meter, like per 1 meter into the page. Got that? Okay, let's do our quiz. Why are you talking shit? Yeah. Alright, is anyone still joining? Nope. Okay, let's start. let's review. So basically, I'm going to draw a diagram. So if you have these kind of two layers of rock that are situated on top of each other for a long time, they kind of have this like equilibrium with each other in terms of this pressure, weight, and this is called the confinement pressure, right? What the top rock layer kind of does to the second layer, right? And so when you remove the top layer, you get rid of the confining pressure, right? Rock 2 is actually going to want to do this uplift, or it's called unloading, de-stressing, right? And so yeah, that's what we're talking about there. Which is not considered a form of mechanical weathering. So basically rusting is a oxidation, which is a chemical reaction. Acid rain is kind of both mechanical and chemical. So sorry, that one's like not very clear. Freeze thawing is still a physical process. So when water turns to ice, there's actually no chemical reaction which happens. It's just a physical phase change, right? So yeah. And yeah, this one's just like kind of understanding the words. The first one's the one that's right. The second one, I switched around alluvial and aeolian, and then some of the ones on the right are just like complete BS. Soil strength, yeah, is based on shear strength. So kind of think of it like this is the best analogy I can come up with. So if you have a big bucket full of tennis balls, right, and you jam your hand in there, what's going to happen is these tennis balls are going to slide off of each other, right? So that's essentially what's happening with soil, rather than the individual tennis balls like compressing and becoming deformed and stuff, if that makes sense. So that shear strength is usually the limiting factor for soil design, right? Soil's generally a much weaker material than stuff like concrete, for example. And yeah, so this is another definition thing. It's not to do with the hydrostatic water pressure, drained and undrained conditions. It's to do with the soil itself and how permeable it is, I suppose, and the fact that if water is able to flow or not flow through it. Sorry, permeable might be a bit misleading, but yeah, it's to do with like, is water able to freely flow in and out of the soil? Yeah, here's some drawings. All right, cool. So I'll give you guys Smoko until 11:50, but first we have some reps from SevSoc or I can talk about it if you like. Yeah, so our general will come up, we'll talk about industry mentoring. Did a couple of you guys come to Careers Fair? I think I saw some faces. Careers Fair was the other day. Hopefully that was useful. But industry mentoring is a program. I'll give it to Arjuna to talk about it.
So SevSoc is holding another program starting in term 2, but applications are open now. For industry mentoring, we'll get paired up with an industry rep that is from one of like the big civil engineering companies, and throughout like a whole 4-month program, you get to know like tips and tricks about how to boost your resume, boost your interview skills. You may even get a job like straight away. That is not. It's not guaranteed, but it can happen. It has happened before. Yeah. But yeah, there's like there's like 4 checkpoints during the program that you meet up with your mentor that's assigned with you. And yeah, it's just good vibes as well, because it's not as like a professional setting as much as like Careers Fair or something. You still get to have a good interaction. You can like meet up with your mentor at the company's head office, and get to know the company a bit more like through your mentor. But yeah, applications are open now. They close 1st of April. So if you want to apply, I suggest that you do.
Yep. And correct me if I'm wrong as well. And the mentors they get paired up with, they're not like super senior in the company, so it's like not too hard to relate to them. As well as they're not too young, so that they do have a bit of experience. They're kind of in the middle of the career.
They're all graduate engineers, just not senior. Like some are senior, like 1 or 2, but technically across the board. And it's one mentor per mentee. It's like one-on-one interaction.
Yeah, fantastic. Thank you very much, Angela. Alright, all good. We'll continue at 11:50.
Why did you say that?
I realized what you said. You should do it so you can grind it in. Maybe grind is something nice. I got in trouble when you have 무슨 샤우팅이 나왔어요? Maybe this is the end. Actually, every event I show up to, he didn't show up to, but every event he showed up to, I was in there. So we never actually met at these events.
Beyond what
What?
He's gonna be mental.
I'm gonna be graduated like halfway through this program. Yeah. Why did you pick me as a director? Like, what's fucking wrong with you?
He graduates halfway. I'm during road trip, he's gonna graduate.
Wait, I seriously? You don't need
What?
He can be mental. He can like mental.
Oh no, I don't think my grad program would start until next year anyway. No. If I go on, you know what I mean? Like most grad programs start in February.
You want to do an extra couple courses so you can stay in term?
No, I might teach in term 3 if that's the case. Sorry?
Pick up architecture.
Yeah, you know what? Never too late to start.
Do commerce again. What? It's good knowing you, Henry.
I'm gonna die. Hang on.
You visit him in the office.
You'll be
Yeah, I'm gonna just pass away.
He comes to like the next camp, he'll be like the special guest.
Fuck's sake.
I mean, that's nice to ask as well. Like, when you look at the second and first years,
Alright. We're gonna continue. So basically what I have up on the screen here, for those of you who just is a copy of my notes as usual. Here's a mailing list where I'm basically going to, like, you just give me your email and I'll send you the recordings of me yapping basically, and there'll be like a playlist on YouTube and all that stuff. If you have feedback as well, feel free to include it. The form, you can submit it twice if you want to do it anonymously. But yeah, that'll help to improve the classes as well. So yeah, if everyone's happy with that, I'll move on. Okay. All right. So we're going to be talking about geotech now. So this is applied geotech. So in terms of where you can find these questions, do you know that big booklet, which is like you have the physical copy, or if you don't have the physical copy, it's on Moodle under applied geotech. So at the back of that booklet, that's where you can find the workshop questions now, right? So we're under the topic soil mechanics review, and there's 3 questions. I'm not going to cover the third question today because it's very similar to this question. So we're just going to be covering 2 questions, but I'll cover them quite in depth, right? So hopefully you know what's going on. So the first one is basically the situation. I'll just read out the question. We have the semicircular failure plane basically, right? Which is this line here. And we have a long strip footing, right? Which is this blue rectangle here, right? So we're looking at the 2D version of this question. Here on the right, I've drawn it out. So strip footing means that that length which runs into the page is much bigger than our width or our breadth or whatever, right? And we're going to be analyzing this question under undrained conditions. And we care about point O because the failure is going to rotate about that point. So that's this point here. That's point O, okay? So first I'm going to give some context. Yeah, what we're looking at is a footing. And so a footing is usually made out of reinforced concrete. And it's a foundational structure, so usually there's something on top of it, which usually a lot on top of it, which gives it a lot of loading. In terms of what we're going to be analyzing in this course, we're not going to care about the strength of the concrete, essentially. If you go on to do advanced concrete, in that course, we look at this whole setup again and analyze the ultimate capacity of the concrete itself. But in this course, we actually care about the bearing pressure of the soil, right? Which I'll talk about in a second. But let me just write that in strip footing cases, we have that B is much smaller than L, right? So L just goes into the page for however long. But we're going to do all our calculations in terms of this per 1 meter run. Got it? So as I was saying, ultimate bearing capacity is going to be denoted by Q. So this is essentially our soil strength just before it fails in shear. Okay? So again, Q, nothing to do with the concrete breaking. It's to do with the soil underneath slipping. Okay? We're going to be analyzing this question under undrained conditions, which just means we have to take into account the effects of water, right, flowing through it, which doesn't sound as hard as it actually, which isn't actually as hard as it sounds, because you'll see. And then part B of the question is the same thing, but there's going to be surcharge acting on the soil as well, which I'll explain later as well when we get to it. Okay. So the first thing I have here is, this is a screenshot from the lecture slides. This graph kind of shows you, I don't know, it's like to do with the material properties of soil in terms of its function between cohesion and friction. But you don't need to draw this graph every question. This is more like context of where this number comes from, right? What we need is this formula. And what we're going to be calculating is this left-hand side. This is our soil shear strength, which we need to define, right? So from the question, we're given that Cu is 100 kPa, right? And phi u is going to be 0 degrees, right? And because it's 0, this whole portion cancels out, right? Let me look at it up here. That's these two properties here. Basically, what we're looking at is some sort of clay or something which is primarily based on, primarily gets its strength from cohesion rather than friction, right? In the question solutions, they actually just keep Cu algebraic for now, so that's what I'm going to do. So instead of replacing it with 100 kPa right now, I'm just going to replace it at the end, okay? Here, I'm going to do the biggest tangent of all time, but this will help to explain it, I reckon. For context, right? The first course I ever taught was in term 2 last year, engineering mechanics, and I love to think of everything in terms of engineering mechanics. I'm going to do a quick review of it because this question will require taking the bending moments and understanding that very thoroughly. Okay. So, say we have this simply supported beam, like this, right? And we have this uniformly distributed load on it. Let's call W, which is the uniformly distributed load, 5 kilonewtons, and that's a force that's spread out linearly, so in like one dimension, right? And then we have to give this some sort of length, right? So that's 5 meters, right? If you do the reaction force analysis using equations of equilibrium, find that this is 12.5, this is 12.5. These two reactions will carry the same amount of load. So essentially what's happening, this blue distributed force is kind of an external force, right? It could be from the software to the beam, it could be from the piano or something on top of it, right? This is loading onto this beam and spread out, right? What these are at the support reactions, right? These are in response to your external loading. Essentially, that's what's happening, right? Okay. So next thing we have to talk about now is bending moments. So if I mark some point, say here, 3 meters from the left-hand side, right, let's call that point A, point B, point C, for example, right? If I take the sum of the moments, right, we have to take it about a certain point, right? And just for the sake of this demonstration, I'm going to take it about point B, okay? It's in static equilibrium, so everything's equal to 0. And now we have to add on our counterclockwise moments and subtract our clockwise moments, right? And so, just make that a little more clear. Okay. So how do we do this? Let's look at this reaction force at C first, right? That's the magnitude of the force, of this point force that we're looking at. And we have to analyze, we have to multiply it by our lever arm, right? So essentially what's happening is this is our point of reference B, And this point force has something called a line of action that extends infinitely in both directions, right? And what our lever arm is the perpendicular distance from our point of reference to that line of action, right? Got it? And so that would be 2 meters. And this bending moment is going to be positive because it's causing a counterclockwise spin about B, right? It's coming back. Okay, now next let's look at the support A and its point force 12.5. This one is going to be negative because it's causing a clockwise spin about B, right? And then we're going to multiply that by 3, which is its lever arm, right? Okay, cool. But now we have one more force which we have to talk about, which is going to be the distributed load, right? The 5 kilonewtons per meter. So we can do something called turning a distributed load into a point load using equivalent loads. Okay, so that was just like a lot of words, but essentially you can turn this big uniformly distributed load, which is a rectangular shape, into a single point which acts down the middle, right, like that, by multiplying 5 kilonewtons per meter by 5 meters, which is how long it stretches across, right? So basically that's just 5 times 5, which is 25 kilonewtons acting down. So this is equivalent when we're looking at the entire system, right? And this is going to cause a counterclockwise spin about B, so we're going to add it. Now the lever arm for this, okay, basically we can split up that 5 meters into 2.5 meters and 2.5 meters, and we know that the uniformly distributed load, if we have an equivalent point load, it's going to be acting down the middle, right? So essentially the lever arm here is going to be the difference between that 3 meters from the left to the 2.5 meters on the to the middle of the beam. So 0.5 meters, right? Cool. So yeah, this little calculations didn't really figure out anything of significance, but I just want to show you how, like a refresher of how that works, right? So back to our question. So how this relates to everything is that this system that we have set up is just a bunch of forces or a bunch of distributed loads in 2 dimensions. And so we can do the same thing. We're just going to take the bending moments about point O, right? But before we do that, we're going to convert a few things, right? So this distributed load Q, right, which is our capacity, we can turn this into an equivalent point load, right? So the way we do that is going to be multiplying that distributed load by this distance here, which is the same as B, right? So it's going to be QB. Got it? That's the magnitude of that force. Next, we have one more force of importance, and that's this semicircle, or rather the resisting shear stress or the shear strength of the soil, right? Which is acting clockwise, right? Okay, but we'll talk about that in a second. So let's see how this is set up. I'm going to do the sum of the moments about point O, right? And what we're going to do is these moments minus these moments. So counterclockwise moments minus clockwise moments, right? So in terms of counterclockwise moments, we're going to have QB, right? But now we have to multiply it by the lever arm, right? So the lever arm from point O to that force is going to be B on 2. Right? And now we have to subtract our resisting force, right, which is the soil strength. So our soil strength, right, you can think of this, when we're analyzing this problem in 2D, right, you can think of shear strength like a one-dimensional distributed load, right? So similar to what we did there, except it's kind of, it acts that way. Okay, so this is in kilonewtons per meter run. But again, let's not talk about into the page. So in order to turn this into a force, think about what we're going to have to multiply this by. So before, for a beam, we multiplied this by the length, right? In order to turn it into a equivalent point load. So think about what we had to multiply it to turn it into a force. Yeah, circumference of a semicircle, arc length, right? Yeah, exactly. So let's figure that out. So we know that the circumference for a circle is pi d, right? That's from year 7. And then in terms of the radius, that would be 2 pi r, or our radius is also the same as our width for our footing, right? So we can call that b. So the circumference for a semicircle is just going to be pi d on 2. In other words, it's going to be pi b, okay? So that's going to be our arc length, right? Good. So now we have magnitude. We have lever arm. And this is our magnitude, right? So of course we still need a lever arm, okay? So think about what would be the lever arm of this force to point O. B, exactly. So the width also acts as our lever arm, because you can think of these stresses as like mini forces wrapping around in a semicircular shape, right? And the entire way, a lever arm to that force is just going to be the radius, or our b in this case, right? So that's our lever arm there, right? So now everything's set in place. What we're going to do is we're going to cancel a bunch of these b's out, okay? Because everything's still equal to 0, right? Now we're going to rearrange for q, right? I'm going to get that q is 2. Oh, my bad, almost up. We worked out before that TF in our question is equal to CU, because we don't have any friction angles strength, right? So this is going to be 2 pi CU, right? We know that CU is 100, and so this is going to be 200 pi, which is going to be 628.32. So this is our source strength. Okay, does anyone have any questions? Okay, next, part B of the question was saying that the surcharge, you can assume that the surcharge is acting over the soil, over all the soil, aka where there's not a footing. And that's going to be called QO, okay? So in terms of our system, right, that we care about, we only care about this part of it, okay? So all the surcharge is happening off to the side. It doesn't actually affect our shear slip, essentially, right? What's going to happen is that this portion of the surcharge is going to help resist the soil failure, right? It's going to resist about point O. It's going to resist all the loading from whatever building or whatever this is from the footing, okay? Oops, booty call. Okay, so okay, so next we're gonna do the same thing. We have the magnitude of the building or whatever this is, whatever we're calculating for Q, multiplied by the lever arm, right? And we're gonna also subtract. Okay, let me do this a bit slower. So this is, remember, the equivalent point load. Got it? Here is the equivalent point load for surcharge. Got it? So we're going to do a very similar thing, except we're going to subtract it because this is acting clockwise on our spin about O, right? But it's got the same lever arm. And we do the same thing as before. We're going to subtract off the shear strength multiplied by the arc length, which is pi b, multiplied by the lever arm, which is b. Okay, I'm going to cancel a bunch of stuff. And we also know that the shear strength was Cu. Okay, do the exact same thing. We're going to rearrange for Q, double Q. Oh, sorry. You know what? I'm going to do an extra step. Right? Now we're going to rearrange for Q. Here's the answer. They leave it algebraic, the answer, but we don't know what QO is, but you can plug in CU if it helps. Okay, let's take a sip of water. Does anyone have any questions? All right. Question 2 is going to be quite different, to be honest with you, but kind of the fundamental concepts of the Moore-Coulomb criteria are going to still apply. But instead of looking at bending moments, we're going to be focusing on forces, right? So here's a question. We have a long vertical drain, and then there's this failure of this soil block, right, which is a triangular prism, basically, right? And we have to analyze the safety of the cut, right? So recall soil mechanics, factor of safety stuff, right? The definition of factor of safety is your resisting forces divided by your disturbing forces, right? So if your factor of safety, in this question in particular, is greater than 1, then it's deemed to be safe. If the factor of safety is less than 1, it's deemed to be unsafe. In other words, it's going to fail, right? So usually questions which tell you to analyze the safety will give you a factor of safety they want you to design for, like 2, 3, 2.5, something like that. But in this question, it's just 1, okay? In terms of what we have to do, we have to consider the case where there's no water in the drain. In other words, this is completely dry, okay? And then the other case is going to be where the waters fall to the brim, right? That's scenario A and B, 1 and 2. And for both those cases, we're also going to have to look at the undrained and drained conditions. So there's going to be part A and B for 1 and 2. Got it? And our failure plane is going to be a straight line, but it's going to be diagonal, right? And it's at 45 degrees incline. Okay, so for our first case, this is where we have our drain is completely dry, okay? And there's this, say this drain or whatever is made out of concrete, there's this layer of separation, and we want to look at that soil block. This is a triangular prism, basically into the page. So what a free body diagram is basically similar to this elevation view, except we mostly care about the forces. So the forces which are going to be acting in our system is going to be the weight of that soil block, which I call W, as well as the shear stress of the soil, which wants to counteract that weight, right? So what we're going to do is, just like in those physics questions which have like an incline and you get the boxes and everything, you're going to find it advantageous in this sort of scenario to split everything up into forces tangential to the plane and perpendicular to the plane. If you remember these forces, weight on that box, you kind of want to split it into these kind of components, right? That's exactly what we're going to do, but for the soil. So remember, this is 45 degrees. Here we had W sine 45, W cos 45. So sine 45 and cos 45, like mathematically the same, because we're at a 45-degree angle. But if this was a different number, then that sine and cos would be more significant, right? Yep. Okay, so that's the first step, right? That was a prep. Here's the first step. The first step is use geometry to find side AC, right? That's this hypotenuse, right? So you can do this in two different ways. One might be using Pythagoras, because you know that this is 5 meters, the square root thingy. I've decided to do it using angular geometry. So sine 45 degrees, right? So here's our 45 degrees. The opposite side is 5 meters, right? And then hypotenuse here is AC, which is our unknown. Rearrange for AC, you get that this is 7.071 meters, right? Boom, just like that. Okay. Next, we're still doing prep. We're going to find the weight of that soil block. When I'm talking about the soil block, I'm talking about this triangle, right? So W is going to be the unit weight, right, which was given to us, multiplied by A. We're doing A because we're doing per meter run, remember. Okay, so what is going to be A? A is going to be this area, right? So the area of that triangle is going to be half base times height. We know both sides, the base and the height is going to be 5. That's going to be a number. So we get that this is 275 kilonewtons per meter. Oh, sorry, that's kind of misleading. This is kilonewtons and then per meter run, aka per meter into the page. All right, time to get to formula. So we're going to analyze the undrained safety first, right? Which we have a formula for. So, similarly to question 1, we have that our undrained friction angle is simply 0, so that's good because that means that entire component gets cancelled out. And CU this time will be 30 kPa. Right? Now we can look at the factor of safety, which again, resisting forces over disturbing forces. Okay, so what does that mean in terms of this question? Let's look at our free body diagram, right? We know that our soil wants to slide down the slope, and we know that what is resisting it is going to be the soil strength going up the slope. So that's essentially what we're going to do. Right? It's that tangential component of the weight, which is going to be our disturbing force, essentially, right? So resisting force is tau multiplied by AC. I should probably explain that. So do you remember in the first question, to get that, to convert the shear strength into a force, you have to multiply. You had to multiply it by the arc length before when we were talking about the semicircle. So of course, when it's a straight line, we just multiply it by the straight line, right? And then again, as I said, the disturbing force is the down and left component of our weight, which we've already cooked up already. Okay, so when we punch this in the calculator, we get that this is 1.09, right? Which is greater than 1, which is safe for the purposes of this question. So again, if another question asks you to do the same thing, but the threshold is actually a factor of safety of 2, this would be unsafe, right? All good? Sorry if anyone's still copying this down. Do you need the, like, I've got the QR code to my notes as well, because I don't know if I'm going too quick or anything, because I'm going to keep scrolling. Okay. All right, now we're going to look at the drain safety case. So that's part B. We're still looking at scenario 1, part B of that. So we have a different formula for it. Drain formula, right? You're going to find this number is going to be 27 rather than 0, which means that we have to calculate this, right? Whereas this number is 0, so we can just factor that out. Okay. So, basically, what we need to plug into here is the effective normal stress, right? The effective normal stress has 2 components which you have to subtract off each other, which is the total stress minus the pore water pressure. So let's find the total normal stress first. So basically, we're looking at this failure plane, right? So if I'm looking, that's my eye, right? If I'm looking at this failure plane, it looks like this, or whatever, right? Pretend this is per 1 meter run. And this angle here is AC, right? So what's the normal force acting on that? Okay, so before we were considering the perpendicular, the tangential or parallel force. Now we have to consider the perpendicular force, right? AKA the normal force, which is pushing against this, let me highlight it, which is pushing against this failure surface, right? So that's our normal force. Okay, and in terms of area, it's going to be the area of this failure plane. We're not going to include the 1 meter, it's just going to be AC, right? That gives us that the normal force is 27.5 kPa, right? Makes sense? So U is going to be the hydrostatic water pressure at the middle of the failure surface. Now this is an assumption. So what, usually like in soil mechanics, they'll tell you exactly the height of the water table when you're doing the effective stress calculations. Here, we're not really given any information except that we have to conduct this drained analysis, right? So the assumption that the solutions are given, and I've emailed the lecturer, but he hasn't replied to me yet, as to why the assumptions are in the middle of the failure surface. Just kind of think of it like this, right? Probably helps to do this. We're looking at the soil block, and we don't know, and we know that there's not water flowing through it. Oh, sorry. I don't know how to explain this very well, sorry. But basically, here's the failure surface, here's the middle. We just have to pretend the water table is about halfway up, right? That's it. Okay. That's going to be Z in our calc. So this is 9.8. As we discussed, weight of water. Z is going to be 2.5. Oh, sorry, 5 over 2. Probably makes more sense. That gives us 24.5. Right? All good? So, now what we have to do, since we have this component, we just subtract them off each other, right? (27.5 minus 24.5) gives us 3 kPa. So now we have this one, which is 3 kPa. That's here. Right? Plugging everything in as we did before. Gives us that tau is 1.5286. Right? Yeah, which is significantly lower than 30 basically in our undrained analysis. So yeah, let's just see how that plugs in. Formula is exact same as before. These numbers, same as before. The only thing is that instead of 30, we only have 1.5, right? And if you remember before, that ratio was only just barely over 1. So this number is going to be much less than 1, which means it's definitely going to fail. Okay, so this is for our drain analysis case. Does anyone have questions right now? Yeah. Now let's talk about what happens if our vertical drain is full of water, right? So this whole thing's water. Well, here I've drawn the free body diagram. If you remember from fluid mechanics, hydrostatic water pressure increases linearly with depth, right? And then it kind of results in this triangularly distributed load almost, but it's acting sideways, it's acting laterally. And it's pushing against our, the surface of that drain that we're interested in, right? Okay, cool. So what we need to do is convert this triangularly distributed load into an equivalent point load, right? Which we're going to call FW. And there's a way to do that. We literally just need the area of that triangle. Okay. How do we find the area of that triangle? Let's call this temporarily D. So this is the depth of water, right? If we call that the depth of the water, the way you find hydrostatic pressure is gamma WD. What you've probably seen in fluid mechanics is this version, right? But same thing. So, area of a triangle is half base times height, right? So base is this, height is this, right? We know that D was 5, right? This was 5 here. And this was 9.8, so we can easily calculate FW. And then, of course, this is per meter run. So we've just calculated this basically, right? The equivalent point load of that hydrostatic distribution. What we're going to do is, just like before, we're going to split it up into tangential and perpendicular components, right, relative to our incline from over here. Basically, this ends up being FW sine 45. This ends up being FW cos 45. Yep. Okay. Now, we do the same thing. We look at the undrained safety. If you remember, this was 30 before. This was 0. This whole portion cancels out. So this is just 30 kPa as before. Okay, so this should look familiar. This multiplied by AC over W sine 45, because W, the weight force, is going to be our disturbing force. Then we have the soils resisting shear as one of our resisting forces, but we also now have this diagonal component of the hydrostatic water pressure, which is helping to keep the soil in place, right? So we have to add on that and account for that, right? This was 275, right? punch that in. Remember, without the hydrostatic water pressure, this number was 1.01 or something like that. Now it's 1.5, which is greater than 1. Still safe. Yep. All good? Now we do the drain case with the hydrostatic water pressure as well. So here I've kind of structured it weirdly. Let me run you through what I'm talking about. I want to look for tau, which is our shear strength, right? In order to find our shear strength, we need the effective stress. In order to find the effective stress, we need to look for the total stress minus the pore water pressure. Okay, so now we look at the normal force over the area, which is going to change slightly. Okay, so let's go back to this diagram. We care about this failure surface, right? And we will want to look at all the perpendicular forces to this failure surface, which is going to be this arrow, which is W cos 45, and this arrow. Sorry, I haven't drawn it like perfectly. But those are both supposed to be perpendicular to that surface, right? Right, so essentially we're going to add on these two orange parts. That's here and here, right? And over that area, which is that straight line multiplied by 1 meter into the page, which gives us, sorry, 2.5, this is 275. That gives us 39.75 kPa. U, which was what I was struggling to explain before, was that, right? And it's going to be the same as when we did the drain analysis when there wasn't water, right, in the drain. So if you remember before, this number used to be 27.5, so it's increased a bit due to the hydrostatic pressure. We subtract this one from this one. We get that this is 15.25 kPa. Got it? So in terms of how these numbers plug in, this one plugs in here, this one plugs in here, this one's going to plug in here. These are material properties that were given, right? And now we have 7.77 kPa, right? If you remember what shear stress was for the drain case before, it's something like 1.5, so that's a lot bigger than 1.5, which is good. And yeah, so basically the only thing that changes, so we still have our hydrostatic portion, but the only thing that changes is that this number is different. So before we had 30, yes. Now we have 7.77 and the hydrostatic water pressure, but this results in 0.728, right? Which is still less than 1. So even when the water is in the drain, it's not enough to resist the soil weight, basically. So it still fails. Okay. Does anyone have any questions? So that brings me to the end of my calcs. But I'm still going to explain a little bit of theory. Question 3, this is still question 3. You can try that out yourself. I have my solutions at the bottom of this document, but I'm going to do about 1300 a bit more. Basically, 1300 is really useful. It teaches Newton's laws and just like general mechanical physics, which is useful for basically every subject you're going to do in civil, except maybe like transport and a couple others. But yeah, law of statics, that's the one that goes like sum of the forces is equal to 0, sum of the moments is equal to 0. That means you're in equilibrium, so things aren't moving most of the time, right? Except that there's a rare exception, but anyway. Sum of the forces is equal to MA. This is what mechanical engineers, aerospace engineers, whatever, use a lot. It's where things are moving and you want to calculate its acceleration or whatever. Right? Free body diagram law, that's when you're looking at all the forces on a free body diagram. those are Newton's laws as a refresher, right? So in terms of that first question we looked at, the bending moment one, where there's like the slip failure, we had to find the max soil capacity. We kind of used the law of statics to do that. So basically we took the sum of the moments about O, it was in static equilibrium, and our equation for the Q, like our capacity, was unknown, right? And that's what we had to solve for, okay? But it's in static equilibrium, and that's the point just before the soil slips, overcoming that friction and cohesion component of the soil's like material properties, right? On the right here, this isn't, you're not going to see this in the lecture notes or whatever. This is from 1300. So friction, obviously we have a cohesion component as well, and this is kind of an idealized model, but friction, this is like a friction diagram, right? And so in this domain, this is where we have static equilibrium. Here's where we have things which are moving, F equals ma. So the idea is the point that we were calculating was basically here, just before the whole system starts to slip and move, right? And our resisting soil pressure is going to try to match that, essentially. That's what static equilibrium is, right? So that's kind of how question one worked. Question two, that's when we were looking at the factor of safety and then we're analyzing forces rather than moments. We were looking at the tangential forces basically. And we had our resisting forces and our disturbing forces, and basically F was equal to 0 if it wasn't moving, and F is equal to ma if it was moving, essentially, right? And so what the factor of safety is it's the ratio between this resisting and disturbing force, right? And in our particular question, if the factor of safety was greater than 1 or equal to 1, we're still in the law of statics domain, in that diagram I showed you above, where the resisting forces are just matching the disturbing forces. However, if the factor of safety is less than 1, it means that the disturbing forces are overpowering the resisting forces, causing it to move. So when you have a factor of safety threshold that they want to calculate, it's basically a buffer before it starts moving. So if you have a factor of safety of 2 or 3, that's a bigger buffer than 1, which is, yeah. Anyway, it starts moving instantly after that point. Yeah, cool. If anyone has any questions, happy to answer them. But otherwise, that's it for today. Good luck for your geology stuff. So week 7, Monday, Tuesday, assignment and midterm. I forgot which order it's in. But next, in week 7, so next week's obviously flex week. Week 7 is Easter, so I won't see you in week 7. If you haven't already, please sign up for the mailing list, because I'm going to email over my workshop for week 7 because I can't do it in person, basically, right? That one's going to focus on shallow foundation capacity. The one after week 8 will be settlement, and then yeah, we'll just continue from there. All good. Good luck.
It says